That's what I started doing.
Okay, so this is the first of a few problem-solving sessions. So this is going to be I haven't done this before, so let's just see how it goes. We're going to hold this until 8:30, and it's going to be a pseudo office hour / problem-solving session type session, I guess. So if you guys have any questions, you're free to ask any questions. You're free to answer them too. Yeah. Speak up. Mhm. So, well, yeah, the question was if there are at least two ham paths, how do we infer from that there is a cycle? And it's just seeing that if you have two different ham paths, then the sequence of vertices along the ham path must be different because they're different Hamiltonian paths.
So you can't have like a path, like two paths that go to the same node and then split?
No, I'm saying they differ in one vertex at least.
How do we know that?
That's the definition of having different Hamiltonian paths. That's just a sequence of vertices that you go through,
Yeah.
and by being different, they're not the same.
Right. So like we know that it goes through, like it touches all the vertices, right? That's the path. But
Yeah, that's the definition of ham
so
path.
if you go through an arbitrary node, so like one of the paths that you're through is in one direction, so you can't have another path
Going the other way.
because then it would be the exact same one.
Yeah.
Okay.
But there certainly could be at least two ham paths. And it's actually not too difficult to produce an example for which that is a possibility. But it's just saying if there are two at least, then you have to see that there is a cycle of three vertices somewhere. I can't give away too much. But it's just seeing that because the ham paths are different, then there must be a cycle somewhere. And the fact that it's a tournament.
Okay, so knowing that, we just have to use the fact that the paths are going to be, well, they won't be going the exact same direction, and then you use that as like.
Yeah, two different ham paths can use the same edge. It's just that they must differ somewhere else, obviously. But they can use the same edge.
I guess my question was like, since you use like an arbitrary node, so let's say in the case where they use the same edge, so you're going to be able to find the cycle in that arbitrary node?
I'm not saying you'll be able to find the cycle from the ham path. I'm just the problem says that there exists one somewhere. It's not. It doesn't necessarily involve that particular edge. And of course, there could be many cycles on three vertices. But I'm just saying that there is at least one when you have at least two ham paths. Okay.
So
yeah.
I intuitively understand that.
Mm-hmm.
I have no idea how to prove that.
That's the part of problem solving.
Okay.
Yeah. It's a difficult problem. I will agree with you on that.
Place where I can start.
Try some small examples where you guarantee that there are two ham paths and see where the C3, so cycle on three vertices, where C3 is in that. So start off with four vertices is my, make sure it's a tournament first. Because if it's not a tournament, then I can't say anything. But start off with a tournament, make sure that there are at least two ham paths and see if there is a C3 in there and see how did it come about? Was it because that in the place where the two ham paths were different, or did it somehow involve it where maybe they agreed on some edge? Just see where that C3 lied somewhere. And don't worry, the I don't know does work on that problem.
I did it a different way. If I'm not talking
Yeah.
about those two paths, it's just I'm wrong. Should I just
Okay, go ahead.
go ahead, like, talk about it?
Well, you brought it up.
Okay, well, I'm sort of saying that depending on the number of vertices, that's going to determine if it has a three path or it has a Hamiltonian provided, without going into it too much, the nature of how there has to be directed paths sort of forces it into a pattern. That
Okay,
can't
okay,
be
yeah, I see what you mean. Yeah, if you can prove it along that line, that's totally fine. Yeah, I'm not restricting any way that you can prove it. Yeah. Other questions? Yeah.
For problem 1B, if you've proven that B is a subset or equal to C,
Mhm.
you just say in our submission, if you do the same proof, you're proving that C is a subset or equal to B, instead of having to do the whole thing all over again.
We have to say how to modify it if you were to do that.
Okay.
Hmm. Yeah, but yeah, that would work. Other questions? Yeah.
On the DA part two, for that one, can you just give an example of the string, like as a proof,
Prove that there exists a string.
but like the example of the proof is that not?
Yep, that's perfectly fine, but you have to prove that it is an L.
Well, let's say
Oh.
that it is.
Oh, it isn't an L, sorry.
Okay.
I wrote the problem, somehow I forget it. Yeah, just make sure you prove it isn't an L. Because it's like because you can imply the inductive step in multiple different ways, there may be some weird way in which it ends up being an L. Prove that it isn't an L. Yeah.
So still we have to do some clarification on problem 2.
Uh-huh.
So suppose you have the term with 5 digits,
Mm-hmm.
but the question you're asking is the improvement for the directed cycle with exactly 3 vertices.
No, there's a subgraph that has a cycle on 3 vertices. Okay, so I'm saying that either there exists exactly one Hamiltonian path, or there's at least 2 Hamiltonian paths, because a tournament always has a Hamiltonian path, which means that there must, if it's not one, it's at least 2. In which case, if there's at least 2, there must be a cycle on 3 vertices somewhere. Yeah, I'm not saying which 3. I'm saying there is a subgraph on 3 vertices. Yeah. Other questions? Or we can work on some problems. Yeah.
Do you have any suggestions on how to get started on a problem when you know you have to prove something, but you just have no idea?
Write an intuitive idea down first, and then work from there. And then maybe work out some small examples first, and then try to see, okay, yeah, like the ones that we did over here, where we, I guess way over here, where we had a, where we worked with this computation right here of this NFA, we worked with a small example, and then we tried to generalize it. And then the way we generalized it was we looked at what happened in here. We had some choices that we can make, and so therefore we have a set of things we can do, and so therefore we have Ri plus 1 is a member of that set. So it's just extending what we have done in the example. So working out a few small examples, I really recommend. And using Piazza. Piazza definitely helps. It's been helping people. Use Piazza. Other questions? Or we can work out some examples, or yeah.
I have a non-formal question. If we contribute a lot during class, does that show Piazza commenting?
What do you mean contribute during
Like,
class?
You know how the class participation grade is based on our class participation as well as the Piazza participation?
Yeah.
So if we participate a lot in class but 0 on Piazza, would we get like 50% on that?
Do you think I have a way of noting that?
Just your memory.
I would not rely on that.
I actually could do that, but it's just that it would be hard for me. And it would be unfair, because if I happen to get one wrong, then that's going to cause a huge problem. And that way, so Piazza is the way that we'll try to do participation. Yeah. Yeah. Other questions? This is good. Yeah.
1B,
All about questions 1 and 2.
haven't gotten to the rest.
You haven't gotten to the rest, yeah. All right.
Okay, think through how formal for B. So I'm sort of going over two possible cases and how it's like a contradiction, but
Be-
I'm not going in full contradiction mode.
Be as formal as you can.
Okay.
Yeah, so like let A, B, C be sets with the property that A union B, C equals B union C, et cetera, et cetera, et cetera.
So get rid of like however and just put it there as
Yeah.
it is.
If you were saying like pick an arbitrary element, let X be an arbitrary element of A, or X in A. Yeah. Yeah. Be as formal as you can.
Okay.
Yeah. If it says make a formal proof, give a formal proof. Other questions? Yeah.
Or can we use like make our own like data structure? Is it just only using the graph?
You can, because you're making a pseudocode algorithm, you can use any data structure in addition to the, so you're presented as input the graph, and then you work with whatever data structures you want and output the result at the end. Yep. Just make sure that the data structure is fast. Other questions? Or we can work on some examples from lecture. Okay, cool. So I didn't prepare any, so I'm gonna think of some. So one that I posted on Piazza was all the strings in 0, 1 star, such that 0, 1, 0 is a substring of the string W. Let's make that a little bit, let's do this. So let's let L be all the strings in 0, 1, 2 star. No, let's make it 1 star. So this is one I kind of like. The binary representation of W is divisible by 5. Okay. So an example string obviously is 0. That's in there. 1, 0, 1's in there. What's 10? It's 8. 1, 0, 1, 0. Oh, that's pretty obvious. Okay. Well, let's see. So I'm reading a string from this side to this side. So I'm reading most significant bit first down to least significant bit. And what I want is a DFA for L, not an NFA. It actually won't help here, actually. But now, so what I want is a DFA for L. Okay? So any ideas on how we can approach that? Yeah.
Have like 5 states in the DFAs to represent like what your remainder would be after dividing by 5.
Maybe that's an idea. Let's try to look at all possible remainders when dividing by 5. Well, what are those? 0, 1, 2, 3, or 4. Good. So that's a common strategy that I like for not regular languages, for any of these problems, is to model all possibilities as a state and then connect the states up depending on what happens. So make 5 states, Q0, Q1, Q2, Q3, Q4, where Qi represents the string so far having remainder I when divided by 5. Okay, so that's just an intuitive idea. And we can actually kind of see it if we look at the last 2 example strings I gave above. How did I get from 101 to 1010? I read a 0 afterward, but in binary terms, what does that represent? I shift left by 2, or multiply by what? Multiply by, it's binary. Multiply by the number between 1 and 3? 2. Don't make me work too hard. All right. Well, what if we instead had 101 and 1011 instead? How can I tell? So this one's 5, represents 5. Without brute force calculating what 1011 is in decimal, what is it? Multiply by 2 and add 1. Because it's just the 1010 from before, but we add 1. So we know that for sure that it's 11. What about the remainder? It started off with 0 remainder because 5 divided by 5 has remainder 0. Multiply by 2 and add 1. Without brute force calculating 11 mod 5, what is 0 times 2 plus 1? 1. So you know the remainder is 1. What if I had 8, let's say, so 1, 0, 0, 0, and I read a single 1. So this was 8. What is its remainder when divided by 5? 3. So what do I know that the remainder will be? So I know that this will be 17. But how do I find the remainder from 3? Well, as we said before, we multiply by 2 and add 1 because we just saw a 1. Well, that results in 7. Oh, what's the actual remainder? 2. Oh, how do I get from 7 to 2? Mod by 5. So that's how I find the remainder. So what I have in general is I'm going to have a transition from qi to qi plus 1. No, not I plus 1. To qj if I is on input 0, sorry. If I is, no. Let's just do the actual example. So we'll have the 5 states like I mentioned before. So I'm going to arrange them in this circle pattern just because I can. So what should my start and final states be? Q0, because if I haven't read anything, that represents the number 0. So I should start here. And it should also be the final state because I want to be divisible by 5, which means 0 remainder. So that should be the only final state. Okay, well, from Q0, where do I go on input 0? I self-loop because, why do I self-loop here? Right, so if I see a 0, that represents multiplying the number by 2. Well, if it was divisible by 5 before, does multiplying by 2 change that? No, because it's still divisible by 5. So I self-loop. We're actually subtly using the fundamental theorem of arithmetic here, but I'm not going to worry about that. Q0 on 1. Where should I go? Let's see. If I read a 1, that means multiplying the number that I've seen so far by 2, then add 1, because I just saw 1. Well, what does that mean? If I have remainder 0, and I multiply by 2, we just figured out its remainder is 0. But then I saw 1. So I add 1. Now what's my remainder? 1. So where should I go? Q1. Good. Yeah. Okay, so what are we trying to do here? What we're trying to do is we're going to keep track of the current remainder. because obviously, once I have this machine, I could have a string that's so long that I can't remember the entire number and then figure it out myself later. So I gotta keep track of something that's easy to keep track of. So what I'm doing is what is called modular arithmetic. So what I'm doing is I'm keeping track of what is the current remainder whenever I divide by 5. Okay? So if it happens to be 0 and I see a 0, that means I left shifted the number by 1 position, meaning I multiplied it by 2. So I assumed it was divisible by 5. Multiplying by 2 doesn't change that. Okay? So let's look at an example. So if I have 101, which is 5 like before, that's divisible by 5. So I would be in Q0 at this point. If I saw another 0, well, that number is what? 10, exactly. Is 10 divisible by 5? Yes. What if instead I saw 1011, which is obviously 11? What is its remainder when divided by 5? 1, because if I have remainder 0 when I had 10, then I added 1. It's just modular arithmetic. So I just do the usual arithmetic, and every time I mod it by 5. So if I add 0 to get 1, 1 mod 5 is still 1. Whereas before, remember when I had 7, I had to mod 5 to get down to 2. Because I have to be, the mod is always between 0 and 4. Okay? Does that make a little bit of sense? Or are you just saying that?
Just a little bit.
Okay. So let's work on the other states. So if I'm in Q1, that means the current remainder is 1. And then I see a 0, then what should the current remainder be? That means multiplying the number by 2. So the current remainder now is 2. Oh, so that means I should go to Q2. Oh, from that fact alone, where should I go on 1? Go to Q3. So these problems are nice because once I figured out whatever 0 goes, then 1 is just the next guy in the cycle. Because if I add 1 with a current remainder, the remainder will go up by 1. Okay? Q2, where do I go on 0? Q4. Because 2, when I read a 0, I multiply the number by 2, which means the current remainder now is 4. Okay, so I'm going to go over here. Q2 on 1. Can you tell where I'm going to go? Q0. Good. Okay. Q3 on a 0, where am I going to go? Let's just be sure. Q3, so that means the current remainder is 3. Multiply by 2, the current remainder will now be 6. But now I got to mod it by 5 because it's over 5 to be 1. So now I got to go to Q1. Q3 on 1, where do you think it's going to go? Q0? Q2. Because there's always 1 more than the wherever it went on 0. Q4 on 0. So this will be the hardest one. Well, the current remainder is 4. If I multiply by 2, what's the current remainder now? 8. But if I mod it by 5, it is 3. So then I got to come down to here. And then Q4 on 1 is a self loop. Because if 0 went to 3, 1 is definitely going to 4. So let's actually check to make sure that this is right. So we know 1010 is definitely going to be accepted. So let's try that. So because it's a DFA, I must start in Q0. If I see a 1, where do I go? Q1, that's good. Q1 reading a 0, I see I go to Q2. Q2 reading a 1, where do I go? Q0. And then Q0 reading a 0, I stay there. And therefore, I must accept the string. Nice. And actually, we can actually see how it actually works. The touchscreen works now. All right. We can actually see things happen. If we just look at the prefix of the string so far, let's say the first character, that's just the character 1. It says that we have a remainder of 1 when we divide by 5. Is that true? If I only see the string 1 so far, what is the remainder when divided by 5? So 1 divided by 5. 1, that's the remainder. So we must be in Q1, which we are. Good. Now let's look at the next part. 1, 0. Well, that's the number 2. So where should I be? Q2, which is where we are. Nice. Inch along. 1, 0, 1. That represents the number 5. Good. Is 5 divisible by 5? Yeah, so what state should I be in? Q0, and that's where we are. Cool, and then we check 0 after that. Cool, so just a couple things to keep in mind. So we noted that there are only a finite number of possibilities, in this case 5. We made a state for each one of those possibilities, and then just connected them together. And then we said what the start state is and what the final states are, which there happens to only be one final state in this case. Okay? Any questions about that example? Yeah.
Like, there's a way to do it. Like, how did you deal with the factorial? Because you could do it like finding out the binaries of multiples of 5 and see like a pattern between the 1s and 0s, and kind of like make that. But then how did you do the factorial again?
Factorial.
Like, I mean, not factorial, the remainder state to make those.
Yeah, so all I'm keeping track is the current remainder.
Okay.
So if I looked at the number and figured out what its remainder was, it's going to be one of those 5 possibilities.
Yeah.
And then I just said, okay, if I happen to see another 0, that means multiplying by 2. What could the remainder be? Well, it's just whatever it was before times 2 because it's multiplying by 2. But then I see, okay, if I get over 5, I have to mod it down because that means I could have divided out another 5 in that case. So in the cases where it was less than 5, it was easy. But if it was more than 5, we just modded by 5. Yeah. Other questions? Yeah.
For the sake of creativity, is there another way to approach this problem?
Not that I know of that's easy. We can do one that's not so mathy based, unless there are other questions.
That's not mapping.
Mental arithmetic of binary numbers. For some people, it could be a lot. That's no problem. Any other questions about this, though? Okay, so let's do another one. So let's work with NFAs this time. So I'm going to make the language 0. So I'm going to have 3 possible characters on the input. And W contains the substring 0, 1, 2. That'd be too long. Oh well. Let's change it. I want it to be 1, 1, 1, 1, 0, 0. Why that string? Because the first 3 represent 7, and the next 3 represent 4 for July 4th. There's a nice joke you'll see in the problem set that's along these lines. So W contains the substring that thing. Well, let's see. Suppose that this string W has that long substring in the middle. Do I care what happens before? No. Do I care what happens after? Oh, maybe what I can do is spawn off characters at the beginning and non-deterministically guess, okay, the substring's going to start now, and then go over, and then just spawn characters off at the end. Ah, that actually is pretty easy. So we're going to have a pretty long NFA, but we're just going to spawn off characters at the beginning. Well, it could be a 0, 1, or 2. And then now I need to non-deterministically choose. I'm going to start reading the 1, 1, 1 thing. So I'm going to choose to start reading the 1, 1, 1, 1, 0, 0, and then what should Q6 be? It should be a final state, but is that all I need to do? I need self loops on Q6 as well. So just as a recap, just spawn off characters at the beginning because I don't care what happens before, and then just non-deterministically choose, just start reading the characters of the particular substring, and if I make it all the way to Q6, I don't care what happens after, in which case I'm done. Suppose I did this. What I did was axe the last self loop. What is the language now? Ends in that. So the modified language L prime is all the strings in 0, 1, 2 star. W ends in 1, 1, 1, 1, 0, 0. Okay? And if I instead left the last 3 self loops and axed the first 3, what would that be instead? Yeah, it starts with that particular substring. Okay, so these type of problems come up a lot where you are asked, W contains this substring or this substring. And you'll actually see that in your problem set. And the easiest way is to use NFAs. You can definitely use DFAs because we will prove equivalence with DFAs next time. But an easy way with NFAs is just spawn off characters at the beginning, read the thing that you have to read, then spawn characters off at the end in an accepting state. Yeah, you have a question? Yeah. Any questions about that?
Is this enough to just for like to prove that, just put that, and you don't have to put any words, or do you have to like?
Well, what thing would we be proving?
Well, is that just showing that pretty much? You don't have. Never mind.
Well, it depends on the question. If it says produce an NFA for that language, producing an NFA would be enough.
Okay.
Yep. Proving that, show that this is regular, for now, you can only produce a DFA. And eventually we'll be able to produce an NFA. Yeah. Because it may be the case, so let's trace through the computation. That's a great question. Glad you brought it up. So let's move this down. So let's trace through a computation of, use a different color, because I'm patriotic. Let's see, 0, 1, 2, 1, 1, 1, 1, 0, 0, 2. What's there? Oh, you get it? So the question, just for everyone's sake, why was there a 1 on the self loop on Q0? So can anyone answer that? Right. It's just saying I could see a 1 here, Or it could be the case that it's the ones in the starting part of the substring. It's just a non-deterministic choice. If it says, okay, I know that reading a 1 going to Q1 is going to get me to accept, it'll do that thing. But if it says reading a 1 will, at this particular moment, will not cause me to accept, if I went to Q1, it'll stay in Q0. Okay? Yeah, I'm glad you brought that up. Any other questions? Yeah. Between the original and the modified one, yeah. Yeah, so I'll move it back up. Oops. Yeah, so the language I had before was I had self loops on Q6. And what I did was I axed those 3 self loops. And we noted that that language now is L prime, which is W ends in that string. Why is it L prime? How can you tell? So, well, how do you know that L prime is the language of this modified NFA, or is it some other language? How do you know it's that L prime? Right. So think of a computation. If this string happens to end in 111100, then the non-deterministic choices made are up until that point, it'll do that self-loop in Q0, and when it finally sees that 1, it's going to do those 6 transitions over to Q6 and then accept. Well, if there's only one instance of 111100 and there's stuff afterward, well, the only way it could ever accept is if it went down that path, but then it gets to Q6 and there's more input to read. But then what happens? Nothing I can do. So the machine totally stops and it's not a computation now because I couldn't read the whole input. Cool, so it really is L prime. Nice. Other questions? You guys have a, yeah, go ahead.
Why did we include 1 on Q0? Because if let's say we have 1, instead of having 4 ones, we have 5 ones.
Mm-hmm.
That is not part of the
Yeah,
substring.
great question. So if I happen to have something like this instead, so like 5 ones with 2 zeros instead of 4 ones with 2 zeros. So I just put an extra 1 at the front of that example string in blue, right? So what is the computation going to do? Well, it says that the first one could either go over to Q1 or it could stay in Q0. It could do either. But will it make the choice to go over to Q1? Well, if it did, it must keep going along this path of transitions. But then when it gets over to Q4, it's read 4 ones, but there's still a 1 left to read. And there's no transition for Q4 on 1 that's defined. So it'll get stuck. So it non-deterministically can guess, okay, yeah, it's going to cause a problem for me because I can't accept that. So it'll do the other one. It'll do the self loop on Q0, and then now it says, if I read a 1 and go over to Q1, I will eventually accept, so it will make that choice. So it's just like saying, if I somehow had the clairvoyance to know that I'm going to eventually accept, I will make that choice. And if there are multiple ones, I will make at least one. But yeah, so on that first one, no matter what this NFA will do, it'll do the self loop on Q0 first. Because if it happened to do the other one, it will never accept. And it'll never make a choice to not accept if there was another way that it will accept. Okay? I know non-determinism is a little bit hazy for some people. I completely understand. But yeah.
This may be a dumb question, but what would be the difference between the NFA that's been drawn for L prime and let's say another
Oh, a great question. So let's do L double prime, where it just has the single string 111100. It's just a single string now. How can I modify my NFA to accept exactly that language, which is only one string? Yeah, take off the first stealth loop. Yep. So that's another point. If you want an NFA for exactly one string, what you do is just make a path of transitions of that string, and then accept at the end. Okay? Yeah. Whereas for a DFA, you would have to handle all of the other states having, like, for instance, Q0, Q1, Q2, Q3 don't have a transition on 0, or 2 for that matter. So yeah, so for a DFA, this would be a little bit more challenging to do. So that's why NFAs are better.
On the daily exercises, the short answer, the fourth one, given the DFA, where the initial state is not in the final states, what can we infer about the language? Oh, you know what? Sorry. I was going to say, initially...
No, it's a great question. So
I found out what it initially, I misread the question wrong. Initially, I was saying, what can I infer? I said, oh, I inferred that the machine must have multiple states. However, that's not what the language is. The language is what, and so...
Well, it actually doesn't have to have multiple states, because it could be a DFA that just loops on everything, say 0, 1.
Okay.
It doesn't necessarily have to be, it doesn't have to be a final state, and it could be that the DFA has no final states at all. But it's a good point you brought that up. If Q0 is not a final state, what can I infer about the language? Well, that NFA, that DFA accepts nothing. But in general, if the start state is not a final state, what can I infer? Doesn't have the empty string. So the empty string is not in the language. But I can't infer anything else from a DFA. Great point you brought that up. What if I had an NFA that had its start state not a final state? Can I conclude the same thing? I'll give a counterexample. So just because its start state is not final doesn't mean it doesn't accept the empty string. For a DFA, that is true, because every transition must read a character. But for an NFA, that's not necessarily true. Yeah, that's actually the problem that we saw when we did when we came up here, when we did star. If I made that state that the original start state final to get the empty string, which I need to have, I may have a non-empty transition out and back, or actually just a self loop maybe, and then I will accept it because it's a non-empty transition. So it's exactly the same problem that we had earlier. This is really good. I should do this more often. Other questions about that? Yeah, go ahead.
Just on 5, just want to be sure I'm trying to draw the K-choice tree, and the definition is a little, yeah, can we just see one?
Yeah, so K-choice tree.
Yeah.
So this is Q5 on the problem set 0, I think, yeah. So K equals 0. One vertex, easy. K equals 1. That just says take 2 K minus 1 choice trees, which is 2 vertices. All right. And it says arbitrarily connect the root of one of the trees to the root of the other. So let's just say I choose this way. So this is the new root. But I'm not saying that you have to do it this way. I'm saying you can do it the other way as well. So there are many possible k-choice trees in general. Let's do k equals 2 for convenience. So I'm going to take two k minus 1, or so one choice tree. So I'm going to take two of these guys. So I'm going to draw it better. So let's say I happen to do it this way for this one and this way for this one. And now the rules say I'm going to, so this is the root 1 and root 2. And now I'm going to arbitrarily pick one root to be the child of the other root. So let's say I pick R1 to be the child of R2. So this is the new root. But I could have easily chosen the other way.
Okay, so I have a little draw. Can I just
Yeah.
show you this?
Mhm.
I think it's like, so I had a 4
Mhm.
and a 3, and that's a 3. Like it's not complete,
Yeah.
but
Mhm.
then thered be a 2, and the 2 coming after that, and a 1.
Yeah, because of the definition of that
Yeah.
the root's connected. The k minus 1 tree
Different
is
stack.
connected to a k tree. The two k minus 1 trees are connected with one additional edge, as one root's connected to the other.
So this is
Yeah, that's a way to think about it. Yeah. Mhm. And then you'll prove that a k-choice tree has exactly 2 of the k vertices and the other 2 subproblems. Which it seems pretty intuitively obvious because take 2 k minus 1 choice trees, and then when I put them together, now I have twice as many vertices as I had. So it seems intuitively obvious, but you have to prove it. Okay? Other questions? Yeah.
I was intrigued on the back to the daily problems. The cardinality of the language for the what is it? And it's where we said because I came to the same conclusion. I forget who had mentioned it as well, that if you let the final states rather be the empty set, then your cardinality could be 0
The cardinality of what though?
of the let me see.
Is the number of subsets.
The alphabet of a DFA must have.
Oh,
cardinality.
great question. So if you saw my little note under that, it's so this has a little bit of a confusing history. So we offered this problem as one of the on a quiz in a previous semester where we asked the alphabet must be non-empty of a DFA, and we thought, well, no, it could be empty, but the book says it must be non-empty. So we had to award that point back. So it's a great point to think about. So I'm going to stick to the book and say that the alphabet must be non-empty. But let's think about what if it were empty. Okay? So what if the alphabet for a DFA is the empty set?
I mean, you don't have the alphabet is our transition, right? Or
Yep.
so if you didn't have your
So there are no
essentially not
transitions.
You're not a machine. I only can think of it being like a short in a.
But well, let's think about what can happen. So can I have any transitions at all? No, because there's no character to transition with, so, because it's a DFA. So, but I must have a start state because I've defined DFAs to have a start state. So I must have a start state, but I can't go anywhere with it. So what are the possible DFAs?
Either accepts the empty string or not.
Accepts the empty string. We'll get back to that. So the language is what for that first one? What strings does it accept? Empty set. It doesn't accept anything. So empty set. Well, the other possibility is, well, we could have Q0 being final, in which case L is what? It's just the empty string. What is empty set star? Well, by definition of star, that's just the empty string's always in there, union, the empty set, union, empty set, union, etc. That's the definition of star. What is all this? Empty set. What is the empty set union anything? The anything. Ah, that is empty string. So, does this DFA right here, does it accept every possible string over this alphabet? Yes. So it accepts sigma star. But that's empty set star. So you could prove that empty set star is just the empty string, the set containing the empty string, but this is in fact another way. And through all this debacle and seeing that the book was different than what we thought, we actually were able to prove something different in a different way. I think that's pretty cool. I get goosebumps talking about that. Yeah, what? Yeah. I actually, I mentioned in Piazza that I sent an email to Michael Sipser about that, and I never heard back. So it might be in the next revision. I actually sent him something else, but he responded to that, so I don't know. But yeah, that's it's a very interesting question on why an alphabet, what in the book says it must be non-empty, and what I think, it doesn't really say, but I think what it means is that you must be able to execute some transitions. But mathematically, there's clearly no reason why you can't have that. Other questions? Yeah.
So what's going to be the difference with the DFA that you set loop? Let's say that you put a set loop with that.
Well, I can't put a self, in this case, I can't put a self loop because the set of characters, sigma, that's empty. So I need to have a transition over every single character in the empty set, but there's no characters. So I can't ever have any transitions, unfortunately. In fact, these are not the only DFAs. I could have isolated states otherwise, but these are the only two languages. Another great question. If L is regular, how many, so this will be the final question, how many DFAs recognize L? Well, definitely at least one, because that's the definition of regular. But how many? DFAs. Yeah, it's infinitely many.
You could just throw in useful states.
Exactly. So if I have this DFA right here, whatever it does, I can just put states that loop on everything. Over and over and over as many times as I like. Does that change the language? No, because there's no way to get to the state anyway. And is there any reason in the definition of a DFA why I can't have a state out here like this? No. As long as every state has a transition on every possible symbol, we're all good. And those satisfy the definition. So since I can do this as many times as I like, infinitely many DFAs. So if there are non-regular languages, there's either 0 DFAs for it or infinite. There's no in between, which is pretty cool. Any last minute things? Oh, cool. Thank you for saying this was a great idea. So I'll do this in my, so I'll be doing these every office hour. So Monday, Wednesday for the whole semester, yeah. Yeah, I post everything on Blackboard. Any other last minute questions? Yeah. See you Wednesday.